All right, and welcome to the last set of videos with Unit 4. They're all linked together. As you watch the videos, you are able to start the homework as you go, but I've grouped all the videos together because they really address the same concept, and it's important that you're able to pull them out and decide which piece of information or what process am I looking at here. So that's why they're all grouped together. So as you watch the videos, you still are going to be able to do the homework. You don't have to watch all the videos first. The homework is set up such that it's in a certain order, and then the handout at the end of this mixes everything together, so it tests your ability to address which type of question you're dealing with. So what's the goal for this particular segment of video? I want you to be able to use your previously learned concepts, so that's derivatives, and I want you to apply them where related rates are involved. And related rates are easier shown with an example than trying to put a definition to them. So first example then, jumping right in. If you have a calm water and you drop a pebble into the calm pond, a ripple wave will be created, and it's traveling out at 15 centimeters per second away from the center of the circle. Determine the rate of change of area when. So before we get that far, let's talk about that 15 centimeters per second. What does it represent? All right, we got to identify that. So if I look at the ripple wave, okay, and that wave is expanding out in all directions, what is changing at 15 centimeters per second? That's what I want to know. And hopefully, I see lots of hands up, so that's a good sign. When we're talking about a circle, we're talking about the radius. So in the end here, we're talking about the change in radius with respect to time is 15 centimeters per second. So that's what's changing, or that's what 15 centimeters per second represents. So as you get through these word problems, you're going to realize that you need to tie a given value to a variable or to a rate that you can connect. All right. So A part, determine the rate of change of area when the radius is 5 centimeters. So I would have handed out a grade 9 formula sheet for those that aren't sure, but area of a circle is approximately A equals pi r squared. So we want to know the change of area. Change of area is the change of area with respect to time, so dt, and it's equal to, if we take the derivative of the right side, we are looking at 2 pi r dr by dt. So I took the derivative of r with respect to time. Next question I ask myself is, do I have all the information needed? 2 and pi are just numbers. R is given in the question. dr by dt is defined up above. So now we're just plugging this in. So 2 pi times 5 times 15. So we end up 2 times 15 is 30. So 150 pi centimeters squared per second. So therefore, when the radius of that ring is equal to 5 centimeters, area is increasing at 150 pi centimeters squared per second. So that area is ballooning out or expanding at 150 pi centimeters squared. Oh, it's not. Yeah, per second. All right. All right, so the next question then. So B part with this, the area is 400 pi centimeters squared. So there will come times when we're looking for change in area, and we already know that. So again, I'm going to write out what we determined in part A, and we ended up with 2 pi r dr by dt. So when we look at the information, again, 2 and pi are just numbers. I know them. dr by dt is given above. So in this question, or in this part, I don't know what r is. I know what area is. So there will be times where you need to go off and work on the side column to determine a missing value. So we are given the area of the circle, and we know it's 400 pi, and we know it's equal to pi r squared. So we know the pi's will cancel, and to get r by itself, we're looking at the square root of 400. So we take the square root, and we get r equals 20 centimeters. So that was the piece of information that was missing. So now I can determine the change in rate of area with respect to time, because it's now 20, and that dr by dt is 15. So now we end up with 30 times 20, so that's what, 600 pi centimeters squared per second. So therefore area is increasing at 600 pi centimeters squared per second. And the last one is 4 seconds have elapsed. So again, I know my dA by dt is 2 pi r dr by dt. I'm told that time is 4 seconds. So how does that help me? Well, we need to find, again, the missing information is the radius. So how big is that radius at 4 seconds? For the physics students, we know that d equals vt, but people will be able to say for every second it goes 15 centimeters. So that wavefront's just a velocity multiplied by 4. So we're looking at 60 centimeters is the radius we're calculating here. So now we can go to the formula and sub in the information. So this example, while it seems some of you might be thinking it's a little bit trivial, it shows that you may have to go looking for information for missing value, and there's multiple ways to do it. Because in each case here, we were looking for a radius, and you had to go in different directions in order to find each one. So that's 30 times 60, so that's 1800 pi centimeters squared per second. All right. So this is kind of our jump off point, or our basis for all future questions as we move through the unit. All right. So next example here is kind of your traditional calculus question, and diagrams do help. I can't stress this enough. So take your time and draw a nice diagram when we start getting into something that's easy to visualize. So sand from a conveyor belt is being piled. The radius of the pile is always 3/4 the height. So for people that don't know what happens when you pile sand, it forms a cone. All right. So we got the sands being piled. The radius of the pile, so here's radius, is equal to 3/4 the height. So there's my height. So I've been given a relationship here. I know that radius is equal to 3/4 the height. So I want to write down that information. So I have that taken care of. The sand is being piled at 1/2 a cubic meter a minute. 1/2 a cubic meter per minute. Now we've been given information. We have to figure out what is that variable. What does this represent? 1/2 a cubic meter per minute. So now this is where you use your interpretation skills. You know that you're dealing with a rate. So meters cubed. Hopefully most people are saying it's volume, volume. Good job. And the bottom, or the denominator, is in minutes. So this represents the change in volume with respect to time. 1/2 a cubic meter per minute. At what rate is the height of the pile growing at 3 minutes? So we know time. We know t is going to equal 3 minutes. What are we looking for? And this is the other hard part of the question. Okay, it's always the challenging part. What are we looking for? We are looking for rate. So that means it's going to be a fraction. At what rate is the height of the pile growing? So that means we are looking for dH by dt. That's our unknown. So now you look at the information given. We have height, we have volume, we have radius. So we are going to use a volume formula. So volume for a cone is 1/3 pi r squared h. Now, if you look in the question, what do we want to find dH by dt? This is what we want to find. If I was to take the derivative of this right now, all right, so don't copy this down for the people that are angry. If I take the derivative, I know I'm going to end up with a dV by dt from the volume. I know that if I take the derivative of r, I'm going to get a dr by dt, and I'm going to end up with a dh by dt. So I'm going to end up with those. Are they okay, or are they, all right to get? I'm looking for dh by dt, so that's okay. I'm given dv by dt, so that's not a bad thing. I know nothing about dr by dt. Okay? I know what the radius is, which might come in handy, but I'm not given a number for dr by dt. So what that tells me is A, I have to find it, or B, I have to get rid of it. One or the other. Now, I've been given what r is equal to in terms of h. So this is where we're going to do a substitution and just get rid of r. So if we let r equal 3/4 h, we're going to end up with a formula that has no r in it, and therefore I don't have to take a derivative of r, which henceforth you do not end up with dr by dt. Oops, don't forget the squared. So we'd end up with 1/3 pi multiplied by 9/4 h squared times h. So cleaning up my volume formula, my volume will be 9/3. Okay, I'm going to reduce this a little bit here. So I'm going to end up with 9/12. Okay, 9/12 divided top and bottom. So you end up with 3 pi over 4. And that's going to be multiplied by h cubed. Oops. Oh, caught myself this time. Everyone's thinking, oh, another mistake. Nope. Hey, 4 squared. That's not 4, that's 16. So 3 pi over 16 is what that would reduce to. And we'd have h cubed. So this is the volume of a cone when the relationship with radius and height is 3/4. All right. Now I'm all set. Take the derivative with respect to time. 3 pi over 16 is just a fraction. It's just a coefficient. So 3 pi over 16 is going to remain untouched. 3 h squared dh by dt. So here we are. Solve for dh by dt. And when we get dh by dt, so I'm going to isolate here. dh by dt is dv by dt divided by be 9 pi over 16 multiplied by h squared. All right. So there's our volume, and I just divided both sides by the 3 pi over 16 times 3 times h squared. So there's dh by dt. Do we have all the information? Well, I know dv by dt. That's given. Do I know the height? And that's your next question. Do I have the height for this particular problem? And the answer is not quite yet. Okay? So this is why people get a little bit frustrated with these questions because, whoops, don't want to do that, because sometimes it requires some extra work here. So how do I find my new height? How do I find my new height? So at this point in time, I have an expression for how height's changing. So I'm just going to change colors for emphasis. Find height at 3 minutes. Well, can I find the volume at 3 minutes? And that's kind of what we're looking at. The answer is yes, we can find the volume at 3 minutes. And I'm going to leave it there, and I'll finish it up in the next video and just continue on. And what you're going to find, the videos are just going to be a continuation of each other until we reach the end of my examples. And like I said, you'll see whenever we indicate a new goal that you're going to be okay. You can start the homework for the next day, but you can pretty much take the videos done, get the notes done, and then just keep working on the homework.